The extreme value theorem guarantees a global maximum and a global minimum, provided the function we're looking at is continuous and the interval we're working with is closed. And so natural questions to be able to extend this idea of locating global extrema would be, what happens if the function's not continuous? What happens if the interval's not closed? And so I just would like to cover kind of by example in pictures of things that could happen for each one of these cases. And so perhaps we've got a nice function like 1 over x here. It's nice everywhere except for a vertical asymptote that would be at x equals 0 there. But we see it's not continuous. So this function here, this is f of x, equals 1 over x, a function we can write out nicely, a pretty simple rational function. And what we notice is if we are including that place of discontinuity, we're going to run into trouble with a global max and or a global min, depending on what our interval is. And so, for instance, if we're looking at the interval, let's say closed interval 0 to 1, we are going to not have a global max because we have the right-hand side of this graph, which goes off to positive infinity as we approach 0 from the right. And so we have no max, but we would have a min there. I mean, there is a min that would be at x equals 1. Because other than the place x equals 0, the function is continuous, and so it's just we get no max because of the function going off to positive infinity there on the right side of 0. Likewise, if we were to instead look at kind of the left-hand side of 0, we would have no global min because the left-hand side of 0 is trailing off to negative infinity, so we would have no min there on the interval to the left of 0 that we could even say would include 0, but we would have a max. The max would actually happen at x equals negative 1. Okay. And then notice that if we included both sides then, so let's say negative 1 to 1, we would have neither a max or a min because we have both the arrow going down to negative infinity included and the arrow going up to positive infinity. So we would have no max or min. So it really still depends on the interval that you're looking at. But notice this was just one place of discontinuity. I mean, another thing that we could look at would be perhaps we would have, maybe this would be like a parabola with a hole in it. So let's say that peak point that we would expect would have a hole in it. And so let's just, so that we have some numbers to look at, let's say that hole is happening at 1, and that would have been the local max, which would also be the global max, provided it was in the interval. And so notice here, our problem place, our only problem place is at 1 there. That's our only place of discontinuity. So what we really have is if the interval includes 1, so if the interval includes x equals 1, there would be no global max. And what breaks it really is the hole would have been the max if the hole wasn't a hole. It's the place that we would have the peak if it were there. And so you can always create these trouble spots if you're going to not have a continuous function. And so basically you can exploit the fact that we have not a continuous function by taking what would be a max or a min and instead just taking that point away. So that's one thing that we have visually if we aren't looking at a continuous function. And in some sense, the what if the interval is not closed question is very similar. Because if we're looking here at a picture that would have a max and a min, but we took it away, then we're going to have trouble. So right here, we're kind of using the same idea that we had in the previous example, where it would have been a max, we have an open circle instead. So I'll say that would have been a max. But see, the interval would be open here and perhaps closed here, whatever those values are. And so if we take out an endpoint of an interval, it's like taking out the top point perhaps, or perhaps it's the bottom point, depends on what your function looks like. But with that openness on one of the sides, at least, of the interval, it gives you some wiggle room to have points that are missing. And that could even be utilized in a similar sort of way if instead... instead of just taking out a hole kind of artificially not including it, by not including this endpoint, we could also even have like a vertical asymptote that our function would be approaching. So again, it's shooting off to positive infinity there, so we wouldn't have a max on this interval either. Even though it would be closed on one side, having that open side of the interval gives us freedom then for our function to do things that don't kind of contain it into this this restricted max and min for the whole function. And so really what we've done now is we've asked the question, what happens if it's not continuous? What happens if it's not a closed interval? And the answer is we are not guaranteed a global max and min. And just because we're not guaranteed it doesn't mean it couldn't have it. So we could actually have a function that's not continuous where the place of discontinuity is not like a candidate for a max or a min. It's just somewhere else. And so we could have a not continuous function having a global max and min. And likewise for if we were to throw out any of the endpoints of a interval so that we don't have a closed interval, that also could not come into play. It could just be that was kind of a middle point and we reach a highest and lowest point somewhere else. And so it not being guaranteed is very different than it never has it. And so just realize that by taking away the continuity of the function or the closedness of the interval, all it does is it takes away the guaranteedness of the conclusion. It could still happen, but we just don't have that guaranteed.